Namaskara. We have been discussing about the merge sort and the formal analysis of the merge sort. We have seen the historic importance of merge sort. Let me briefly recap what we have done and basic math and the properties, and then continue with our discussions. Okay. So, the divide and conquer algorithm will have the following structure. You are given an input that is split into two disjoint parts and you solve them individually through recursion and then use the solutions to generate the solution of. So, in merge sort you are going to sort A 1 dot q and sort A q plus 1 dot n, and then you are merging the sorted sequences and then obtain the final result. So, if Tn is the number of comparisons done by the merge sort algorithm, then this is T floor n by 2, this will be T seal n by 2 and this will be n minus 1. Therefore, we get the equation T of n is T of floor n by 2 plus T of seal n by 2 plus n minus 1 if n is greater than 1, and T of 1 is 0 because to sort a single element you do nothing. How do we solve this equation? We are now in the process of solving this equation exactly. We have got upper bounds. Now we are going to solve it exactly, and towards that we require certain basic properties of floor functions and seal function. The first property is floor n by 2 plus seal n by 2 is n for all positive integers, right. This is true, and we also have floor n minus 1 by 2 is seal n by 2 minus 1, and we have floor n plus 1 by 2 seal n minus seal n minus 1 by 2. Floor n minus 1 by 2 we have checked, and seal n minus 1 by 2 is same as floor n by 2. We can also show that if you have the following floor n by 2, you divide by 2 again you take floor, this is same as taking floor n by 4. This can be generalized. There is a very simple way to generalize this for P and Q. Seal n by P divided by Q, again taking seal is same as taking seal for okay, you can show that you take seal n by P divide by Q and take again seal, this is same as taking seal n by PQ. This is easy to prove, straightforward cases. Okay, these are all some of the facts and basic properties of the floor function and seal function that we require. Okay. Let us see how we are going to use this. So, we have computed T of n minus T of n minus 1 is T of n is T of floor n by 2 plus T of seal n by 2 plus n minus 1 minus T of floor n minus 1 by 2 minus T of seal n minus 1 by 2 plus n minus 2, sorry, minus n minus 2, this minus. I am subtracting T of n minus 1 minus n minus 2. We have just now seen the properties of floor n minus 1 by 2 and seal n minus 1 by 2. If you look at the previous one, here you can see the floor n minus 1 by 2 and seal n minus 1 by 2. Seal n minus 1 by 2 is same as floor n by 2. So, you can see that these two are same and then they cancel. And from n minus 1, when you subtract n minus 2, you get 1 as a remaining value. Therefore, this is same as T seal n by 2 minus T seal n by 2 minus 1 plus 1. Okay. That is because floor n minus 1 by 2 is seal n by 2 minus 1. Now, if you define d of n, the difference, as Tn minus Tn minus 1, the left hand side is simply d of n and the right hand side is, this is d of seal n by 2 plus 1. So, d of n is nothing but d of seal n by 2 plus 1. Now, I can iterate. What is d of seal n by 2? D of seal n by 2 is d of seal n by 2 by 2 plus 1 plus 1. Okay. D of n is, you take that value, divide by 2 and take the seal. So, you have another seal here. Okay. So, let me cleanly put that in the next page. We have seen that d of n is d of seal n by 2 plus 1. But what is d of seal n by 2? D of seal n by 2 is d of whatever is n, divide by 2 and take seal. So, you take seal n by 2, divide by 2, take seal plus 1. But this is, we have seen, is d of seal n by 4 plus 1. So, that is what I am going to plug in. So, this is nothing but d of seal n by 4 plus 1 and this plus 1 which is already here. This plus 1 is written here, d of seal n by 2. We can continue. This is nothing but d of seal n by 8 plus 1 and plus 1. That is because d of seal n by 4 is d of seal n by 8 plus 1. The other, so you can see the pattern. If you have a power of 2 dividing n, then that many plus 1s are there. Here you have 2 and plus 1, 2 square and 2 1s, 2 cube 3 ones. That is because each time when you divide by 2, you are adding 1. So, I can write inductively d of ceil n by 2 power k plus k. This is the general pattern. Generalizing, you can write d of n as d of. So, in the kth step, if you go through k steps, this is what you will get. Now, let us assume that 2 power k minus 1 is less than n less than or equal to 2 power k. Let k be an integer such that, because n is going to be between 2 powers of 2. It can be a power of 2 or it can be between 2 powers of 2. Any n, for any n there will be a k like this. So, if it is like this, then n by 2 power k, right. So, we will go only up to k minus 1 stages. We will write like this for the sake of our completion. Going k minus 1 step, d, this is equal to d of ceil n by 2 power k minus 1 plus k minus 1. When you divide n by 2 power k minus 1, you get 1 less than n by 2 power k minus 1 less than or equal to 2, if you divide by 2 power k. So, when you take ceil, it is a number between this, therefore, this ceil is only 2. Therefore, this is equal to d of 2 plus k minus 1, d of 2 plus k minus 1. From this, you see that n by 2 power k minus 1 is a number between 1 and 2. It is a number between 1 and 2. So, when you take ceil, you get 2. That is what you are getting here. When you take ceil, because of this condition, you are getting 2. But what is the d of 2? D of 2 is t of 2 minus t of 1. That is the definition of d of 2. T of 1 is 0 and t of 2 you can show to be 1. Okay. So, let us see, t of 2 equal to t of 2 by 2 floor, which is 1, t of 2 by 2 ceil, which is again 1, plus 2 minus 1, that is equal to 0 plus 0 plus 1, which is 1. T of 1 is 0. Therefore, d of 2, which is t of 2 minus t of 1, which is equal to 1 minus 0, and that is 1. So, d of 2 is 1. What we have shown is d of n is d of 2 plus k minus 1, and d of 2 is 1 plus k minus 1. That means d of n equal to k. But how are n and k related? Recall that 2 power k minus 1 is less than n is less than or equal to 2 power k. So, when you take log k minus 1 is less than log n is less than or equal to k. So, log n is a real number between k minus 1 and k. So, when you take ceil, you get k. When you take ceil, you get k. Therefore, k is nothing but, therefore, k equal to ceil log n. Therefore, this is ceil log n. Therefore, we have got a beautiful formula that Tn minus Tn minus 1, that is equal to Dn, and Dn is nothing but ceil log n. Okay. So, how do we find T of n? We do what is known as telescopic sum. Once you have this difference, we can write down the difference for other values of n, and when you add all of them, the intermediate values will get cancelled. That is why it is called telescopic sum. It will collapse to only the first term and the last term. For example, here let us continue. What is T of n minus 1 minus T of n minus 2? That will be ceil log n minus 1, because Tn minus Tn minus 1 is ceil log n. Therefore, Tn minus 1 minus Tn minus 2 is ceil log n minus 2, and Tn minus 2 minus Tn minus 3 is ceil log n minus 2. In this way, you can write T2 minus T1 equals ceil log 2. So, when you add, you can see that these terms are getting cancelled. So, Tn minus Tn minus T1 Tn minus T1 is sigma I going from 2 to n of log I. Take the ceil log 2 plus log 3 up to log n, all these ought to be added, but T of 1 is 0, this is 0. Therefore, we are getting a very nice formula for T of n. T of n is given by this sum I going from 2 to n of log I. Still it is the summation form, okay, it is in the summation form. We can simplify it further, but this summation is very tricky. You see that there is no cancellation, there is no algebraic calculation you will be able to do and then get it any simpler, right. It is a cute formula, but you find it difficult to simplify any further, and this is where mathematicians have come up with a very clever trick. Okay. It is called the summation by part, and Abel's summation by part, we are going to take a interesting special form of it, and that will allow us to simplify it further. Okay. So, now we are going to do the following. We will write T of n as sigma I equals 2 to log I. In fact, log 1 is 0. Since log 1 is 0, I can as well write this as sigma I equal to 1 to n of log I. This is because log 1 is 0. I simply added a 0 term, but I make it look clean. Sum going from 1 to n terms are added. How do I simplify this? If you simply look at it, there is nothing that is getting cancelled or simplified and then this a very complex sum of ceil values. But there is a very nice way we can simplify this. The key observation is the ceil values of several of them are equal. Key value ceil of several of them are equal. For example, ceil log 5. Log 4 is 2. So, log 5 it will be something like 2 point something. So, when you take you will get 3, and log 6 this will also be 3. Ceil log 7 this will also be 3. Ceil log 8 this will also be 3. we are considering the base 2, okay, log I to the base 2 we are considering. So, see log 8 is also 3. You can see that successive values are all equal, but when you cross over a power of 2, what happens to C log 9? Log 9 will be 3 point something. So, when you take seal, it becomes 4. So, at a power of 2, you can see that the values change, it is 1 more. For others, it is same, it will be 3, 3 and 3, suddenly it will become 4. Then it will remain 4 up to log 16, log 16 to the base 2 is 4. When you take seal, it will be 4, but 17 it becomes 5. Okay. So, at powers of 2 it will jump by 1 number, others it will be equal, it will equal up to the next power of 2, the next value will have 1 more value added to it. That is the property of this seal function. Okay. This observation allows us to apply summation by part. Okay. Abel's summation by parts formula. In fact, the continuous version of it is integration by parts. You know that integral u dv equal to uv minus integral v du, something similar to it. This is a continuous version. What Abel's formula is a discrete version of this. So, what we are going to see is discrete summation by part. This is continuous summation by part, that is integration by part, but we are going to have summation by part, which is very similar to it, the analog of this. Okay. So, let us go to the summation by part formula. Sigma I going from 1 to n of ai, right. You have n numbers that are added, and this is same as n times an minus I going from 1 to n minus 1 of I times ai plus 1 minus ai. ai plus 1 minus ai. This is summation by parts. Okay. It is very similar to integration by parts. There is an interesting connection between this and the integration by parts, which you can. So, it is like u v. Here I have a difference, you do not see the difference because the difference is 1, its a is written as a times 1. So, 1 is the difference between I plus 1 and I, therefore, the sum that I comes here. So, this is it is a difference, that is what ai plus 1 minus ai is here. uv minus integral u dv, right, is same as uv minus integral v du. So, you see the, so this is one function, this is another function. Okay. So, this is the difference between that, and here this is basically sigma a times 1 I equal to 1 to. this 1 is the difference between for this function n and n minus 1, okay, is 1. Therefore, this is like your v du. So, for which one the difference will be 1? The difference will be 1 for n. Between n and n minus 1, the difference is 1. So, you get n a n and then I times this integral v du. So, you can see the analog, it is very interesting. Okay. So, I will not clutter this detail. But even if you do not relate this to summation by part or with integration by part, this formula is easy to verify. Okay. This formula is easy to verify. Let us see how many a_n's are there. How many a_n's are there? Here you have n a_n, here you have n a_n. In the n minus 1th term, you will have n minus 1 times a_n minus n minus 1 times a_n minus 1. This will be the n minus 1th term. N minus 1 will multiply these two terms. So, this is what is subtracted. This is what is subtracted. So, you have n a_n, you have from that n minus 1 a_n's are subtracted out. Finally, you are left with only one a_n. There will be only one copy of a_n. From n a_n, n minus 1 a_n's would have been subtracted and that is going to have a_n plus. How many a_n minus 1's are there? Here minus of minus n minus 1, which means there will be n minus 1 a_n minus 1's. From this n minus 2 a_n minus 1's would have been subtracted and you will be left with one copy of. So, in this way you can see that right hand side is same as left hand side. Okay? A straightforward algebra expanding the sum, okay, will show this. So, this is called the summation by part formula, Abel's formula. The proof is by straightforward, is by easy algebra. Straightforward algebra. Expand right hand side, cancel the term, you will get left hand side. Start from right hand side, prove that it is same as left hand side. That is it, very straightforward. This we are going to apply. How are we going to apply? Sigma I equals 1 to n of ceil log I. This is same as n ceil log n minus sigma I going from 1 to n minus 1 of, okay, I times ceil log I plus 1 minus ceil log I minus ceil log I. The same formula I have applied for a log I. This term is okay, this is clean, do not worry about it. How do I simplify this sum? This is an interesting sum. In this sum, you observe the following. If I is a power of 2, ceil log I and ceil log I plus 1, we have already seen that. When it is a power of 2, okay, let us say what is ceil log 16, that will be 4. But what about ceil log 17? this will be 5. When I is a power of 2, they differ by 1. When I is not a power of 2, they are same. Therefore, what you see is this term, this will be 0 if I is not a power of 2, and this is going to be 1 if I is a power of 2. If I is a power of 2, this will be 1. If I is not a power of 2, that is 0. So, all terms in the sum are 0, only few terms are 1. Which terms are 1? The one that are powers of 2. Therefore, let me write down this sigma I ceil log I plus 1 minus ceil log I. This term, for I equal to 1, this will survive. This is equal to, so I going from 1 to n minus 1. What are all the powers of 2? I equal to 0, that is no, power of 2, 1, I equal to 1, it will survive. So, it is 1 times ceil log 2 minus log 1. The next surviving term will be for 2 ceil log 3 minus ceil log 2. The next surviving term will be 4 ceil log 4 log 5 minus ceil log 4. In this way, the largest power of k, 2 power k ceil log 2 power k plus 1 minus ceil log 2 power k. Only powers of 2 terms will survive. What is 2 power k? 2 power k is the largest power such that it is less than or equal to n minus 1, because sum goes up to n minus 1. So, only powers of 2 terms will be there, all other terms will become 0. And when it is a power of 2, this is 1, all these things are 1. Therefore, this sum is 1 plus 2 square up to 2 power k, where 2 power k is less than or equal to n minus 1. Okay? We have already assumed something. What is that we have assumed? 2 power k minus 1 is less than n, is less than or equal to 2 power k. Right? Therefore, when you subtract 1, 2 power k minus 1 is less than or equal to n, subtract 1. When you subtract 1, 2 power k minus 1 is less than or equal to n minus 1 is less than 2 power k. I am subtracting 1. So, n may be less than or equal to 2 power k. Now, n minus 1 is strictly less than 2 power k. Therefore, the largest power of k, that is less than or equal to n minus 1 will be k minus 1. Okay? So, I am using k again and again to avoid that. Let us is less than or equal to, let us use t here for example, is 2 power t right, 2 power t plus 1 minus 2 power t. Therefore, this will be t. Therefore, the largest power of 2, largest power of 2 less than or equal to n minus 1 is k minus 1. This is the largest power of 2 you can have. But what is k? We have already seen that, which is equal to CL log n minus 1. K is CL log n. Therefore, the sum is hence sigma I going from 1 to n minus 1 of I times CL log I plus 1 minus CL log I is equal to 1 plus 2 up to 2 power t, where t is CL log n minus 1. This is the largest power, and this is equal to 2 power t plus 1 minus 1, straightforward geometric sum of powers of 2, and t plus 1 is CL log n. Therefore, this is 2 power CL log n minus 1. Therefore, this sum has got a beautiful closed form, namely 2 power CL log n minus 1. Now, putting all of them together, t of n, which is equal to n times CL log n minus the sum sigma I equal to 1 to n of that sum we have seen already, which is equal to n times CL log n minus 2 power CL cramming, that is equal to n log n minus 2 power CL log n minus 1. Therefore, t of n is n times CL log n minus 2 power CL log n plus 1. This is a complete closed form formula. Okay? See how compact and clean it is. Earlier it was hopeless. When we had t of n as t of floor n by 2 plus t of CL n by 2 plus n minus 1, we had absolutely no hope. But we found out d of n, which is equal to t of n minus t of n minus 1, and this we found to be CL log n. Then we have to find a sum sigma I equals 1 to n of CL log I. For this we have used the Abel's summation by part formula, and finally we got this closed form. Nice way in which we have solved the recurrence for merge sort exactly. Okay? So, to summarize, we have 3 approaches. We have discussed 3 different approaches. The first one is get a bound for powers of 2 or some suitable increasing sequence. infinite sequence, then use monotonicity and that will give you an upper bound. You can avoid this complication and you can guess some suitable function and prove by induction, guess and verify, but that requires you to guess properly, otherwise it may not work. So we have demonstrated that a very tight function we have used for guessing and then verifying. Then we went all the way to solve the problem exactly, because this is very insightful. We are going to use all of them for our discussions at a later point, okay. And then we have shown that the exact analysis T of n is n C log n minus 2 power C log n plus 1, okay. So we close this session at this point. Thank you.